Good morning, sir.
Good morning. Okay.
Morning, sir.
Morning. So, last class, what we have discussed yesterday, do you have any doubt? Everything all right?
না স্যার
Everything all right.
স্যার কতটা বাকি আছে স্যার, মানে এই ফিল্টার ডিজাইন আর কতটা আছে?
Filter
ফিল্টার
design?
ডিজাইন বলি, হ্যাঁ
ফিল্টার ডিজাইনে এখনো গোটা 10 ক্লাস লাগবে, 10-15টা ক্লাস লাগবে।
এটা অনেক বড় চ্যাপ্টার।
অনেক বড় চ্যাপ্টার, মানে এখানে তো এখন তো ডিজাইনের বেসিকটা শিখছি, এরপরে তো ডিজাইন করতে শিখবো, কাল থেকে ডিজাইন শুরু হবে। এখন তো যেটা ডিসকাস করছি সেটা হচ্ছে we are discussing the fundamental aspects of design, but we will start real design from tomorrow. All right, tomorrow means next class onwards, so it will take another 10 to 15 class to complete this syllabus. Filter design is essentially last topic of your syllabus, and after that you are having DSC processor and FPGA. For that only short notes are there, right? For filter design section you will be having short question, 5 marks question, as well as 15 marks question. So this topic is important, and at least you will get 30 marks in the final exam if it is a no conventional exam paper. Now after COVID, what kind of exam will be happen, I don't know. Okay, so in conventional paper around 30-35 marks. So tomorrow onwards we'll start design. Before that, today we will discuss few more things which I am left with. So last class over we have discussed FIR system and IR system with symmetric and anti-symmetric, with symmetric and anti-symmetric filter response. Then we have discussed what do you call symmetry about n-1/2, where n is the number of samples to be considered for filter design. In other words, they are the filter coefficient, right? Filter coefficient in time domain, right? So in time domain filter coefficient, we can take Fourier transform DTFT, then we can get the frequency response. Okay, so in other words, if some frequency response is given, then if I find the inverse transform, then I can get for different values of n, and this n could be selected on the basis of given parameter, right? On the basis of how many samples you have to design, right? That will be given, I have said earlier. Now today we will discuss something called impulse response of linear phase FIR filter, symmetric and symmetry about the origin, that is n equal to 0. We are talking about digital filters, right? Digital filter means your signal digital, impulse response digital. What does it mean? You mean time domain is integer, time instances are integer. Good morning, sir. As well as good morning, as well as your amplitude, they are also integral values. This is what I understand by digital filter. All right, so if we consider the center of symmetry about n equal to 0, n equal to origin, that means you are having negative time as well, which is a theoretical aspect. In practice you don't have, but in theoretically you will be having negative values of n. You will be having the filter coefficient as well as positive values of n. But symmetry about the origin, it means that with respect to origin, left side and right side, you are having equal number of samples, equal number of samples. This is what I understand by symmetry about the origin. Okay, now we'll take an example. Suppose say n equal to 5. N equal to 5 means n is odd, right? Odd. So first we'll discuss for n equal to 5, then we will generalize for any odd values. Okay, if n equal to 5, then your hn will be h of -2, h of -1, h0, h1, h2. Of course, you will be having, with respect to 0, you are having equal number of points, is not it? With respect to 0, what are the points? H of minus 1, H of minus 2, all right, and H of 1, H of 2. So 2 points right of this H0 and 2 points left of 0. This is what I understand, that odd value of n, and it is symmetry about the origin. Now, if I take the DTFT, this is called discrete time Fourier transformation. Discrete time Fourier transformation you are taking because we are getting the transfer function, right? Transfer function of the filter, because DTFT is the Fourier, DTFT of Hn is your h of e power j omega, and DTFT of impulse response is the transfer function of the filter. Now, what I am writing, h of e power j omega.
আরেকবার বলুন না, লাস্ট কি বললেন?
Okay, let me repeat. I am saying that impulse response, if we take DTFT, this will be the transfer function of the filter. All right. So transfer, if you take the DTFT, discrete time Fourier transformation, or Z transformation, whatever be the transformation of impulse response, this is known as transfer function. And if you take the inverse of your h of e power j omega or h of z, that is called impulse response. The impulse response, once we get the transform, it becomes transfer function, and transfer function, if we get the inverse, then you will get the impulse response. Okay. Okay. Now, from this, if I write h of minus 2, DTFT of h of n, okay, h of minus 2 e power j 2 omega, h of minus 1 e power j omega, h0 h1 e power minus j omega, h2 e power minus j 2 omega. This is finite transfer function because hn is finite. Now, here symmetry condition is given that h of minus n equal to hn. This is a symmetry condition given. There are two symmetry conditions with respect to origin. One is h of minus n equal to hn, and h of minus n equal to minus of hn. Okay, we will discuss first h of minus n equal to hn. This is the symmetry condition. Previously, yesterday, what we have discussed, the symmetry condition was h of n minus 1 minus n equal to h of n. Now, since we are considering the symmetry about the origin, therefore it becomes h of minus n equal to h of n. Agreed?
Yes.
Now what I am doing, I am writing h of minus 2 equal to h2 and h of minus 1 equal to h1. And if I write, okay, h of minus 1 is h1 and h0 equal to h0, so h0 is implied. So I will write h0. Now, if I write h of minus 2 equal to h2, then if we combine these two terms, it becomes 2h1 cos omega, and this one is 2h2 cos 2 omega. Okay, h of minus 2, h of 2, that means 2h2 cos 2 omega. And if I combine h of minus 1, this h of minus 1 equal to h1, so this will be 2h1 cos omega. So this will be your transfer function. Then if I write this, h of 0 equal to n equal to 1 to 2, 2hn cos of n omega. Because if we put n equal to 1, it becomes 2hn cos omega. If we put n equal to 2, then it will be 2h2 cos 2 omega. Therefore, this is the transfer function of the filter. Now, what is the advantage of this assumption? The advantage of this assumption, see, if you know that transfer function equal to magnitude of h of e power j omega into e power j theta omega, and theta omega being the phase. Now, we were considering a lot about the linear phase. Now, if the phase is 0, then there is no question of phase distortion, right? So, this is one advantage out of this, that phase is equal to 0. So, phase consideration is not required for such kind of symmetry. This is one of the major advantage of this kind of symmetry. If the symmetry is about the origin, then you need not consider the phase, because phase is 0 and e to the power 0 means it is 1. So only thing you have to design the magnitude of the transfer function, and this magnitude equal to h0 n equal to 1 to 2, 2hn cos of n omega. All right. So phase is equal to 0. This is one important aspect. Now,
স্যার এই cos টার্মটা তো থাকছে, ওটার জন্য ফেজে কোনো
কি দেখে হবে? এখানে তো ওমেগার ভ্যালু বসাবে। If you put the sub value of omega equal to say 0 to pi, some value of omega. So it will give you some value,
Oh,
0.1, 0.2. So ultimately you will get some magnitude, na?
Hmm.
Okay. So phase term becomes 0 because e to the power j theta omega, if that is equal to 1, which means theta omega equal to 0. Agreed? See, this is
Yes.
what? This is h
Yes,
of
sir.
power j omega. So this is h of power j omega. So this is magnitude and phase. But magnitude is there, but phase is equal to 1. E to the power j theta equal to 1. So theta equal to 0. Is not it? Agreed? So with this, what I can say that this is one of the good approximation or a technique, like h of minus n equal to hn and symmetry about the origin, then you don't have any consideration of phase. If there is a phase, then phase has to be linear in order to avoid phase distortion in the filter. The minimum criteria of designing a filter, you should not have any phase distortion as well as amplitude distortion. To prevent phase distortion, I said the filter should have linear phase characteristics, right? Linear phase characteristics. Now, if the phase is 0, so we don't need to be bothered about the phase and linear phase and all these things. This is an advantage of such assumptions. Okay. Now, for this is the example that I have given for n equal to 5. N equal to 5 is a specific value. Now, for any other value, all values of odd, if we consider, then the symmetry condition with respect to h of minus n equal to hn, symmetry about the origin, then in general the expression will be h0, n equal to 1 to n minus 1 by 2, 2 times hn cos of omega n. Agreed? See, for this example, n equal to 5, 5 minus 1 by 2, 5 minus 1 by 2 equal to 5 minus 1 means 4, 4 by 2 is 2. So n equal to 1 to 2, n equal to 1 to 2, and this is valid. So if I put n equal to 1, 2h1 cos omega, if we put 2, 2h2 cos 2 omega, which is again satisfying this equation. So this is in general, the expression of filter transfer function for a given filter coefficient h0 plus summation n equal to 1 to n minus 1 by 2, 2 times hn cos omega n. All right. So this is in general a filter transfer function for any odd value n. Any odd value n. Agreed?
Yes, sir.
Very
Yes,
good.
sir.
And this is very easier to remember as well, particularly this transfer function. Next, another thing I am discussing, the response is antisymmetric. Antisymmetric and n is odd. And center of antisymmetry is n equal to 0. Previously, what we have discussed, the center of antisymmetry was n minus 1 by 2. Center of antisymmetry was n minus 1 by 2. Now center of antisymmetry is n equal to 0. Right? Okay? Fine.
Yes.
Next. So, if the center of antisymmetry n equal to 0, subject to antisymmetry means h of minus 1 equal to minus hn. Symmetry means h of minus n equal to hn. That is symmetry. Antisymmetry, what we say, h of minus n equal to h minus of hn. Previously also we have seen with respect to n minus 1. Symmetry means h of n minus 1 minus n being the number of samples to be considered for impulse response. So h of n minus 1 minus n equal to hn, this is called symmetry condition. An antisymmetry condition in that respect with respect to n minus 1, and center of antisymmetry will be n minus 1 by 2. In that antisymmetry, what we have written, h of n minus 1 minus n equal to minus of hn. That was the antisymmetry condition during n minus 1 by 2 antisymmetry. Now, if we consider the antisymmetry in a filter design with respect to origin, then we will write h of minus n equal to minus of hn. Agreed? Now, again, if we see in this example that n equal to 5 means you are having 5 filter coefficients. So h of minus 2 minus 1, h0, h1 was 2. Then again, if you take the symmetry with respect to 0, there is a symmetry or antisymmetry. Antisymmetry also means that you should have equal number of points with respect to 0. There is 2 points, there is 2 points. So this is all right. Now, in this example, one is the important thing. Suppose if I want to take n equal to 5, n equal to 5 means n equal to -2, so h of -2 e power j2 omega, h of -1 e power j omega, h of 0, h of 1 e power minus j omega, and h of 2 e to the power minus j2 omega. Now h of -2, with respect to this condition, I will write h of -2, this is equal to minus of h2. H of -2 equal to minus of h2. All right, not an issue. H of -1 equal to minus of h1. It's all right. Now h of 0 equal to minus of h0, which means h0 equal to 0. That is again I have discussed in previous case. If x equal to minus x, then x has to be 0. Is not it? Because any integer or real number or complex number, if positive and negative sign, they cannot be equal. They will be
Yes.
equal only and only if they are equal to 0. Right? So this is a fundamental theorem of mathematics, what you call algebra. So h0 equal to 0. So h0 equal to 0 means you have to substitute h0 equal to 0. Now if I write h of e power j omega, filter transfer function, that I will write minus of h, this equal to h of -2, h of -2 equal to minus of h2. Then I will write minus of h2 e power j2 omega. H of -1 equal to, I will write minus of h1 e power j omega, and h0 equal to 0, and h of 1 equal to h of 1 e power minus j omega, h2 into e power minus j2 omega. Then if you combine, then it will be, see, e to the power j2 omega with a negative sign, and minus is a positive sign. So if you take a negative sign here, then it will be sine omega, 2j sine omega. So I will write, combining this term and this term, I will write minus 2j h of 1 sine omega. And if I combine this term with this term, I will write minus 2j h2 sine 2 omega. Agreed? Agreed? Now 2j, so it is minus j, right? Minus j means you have to write e to the power minus j pi by 2. E to the power minus j pi by 2, e to the power minus j pi by 2 means cos pi by 2
cos pi by 2 minus j sin pi by 2
minus j sin pi by 2. So minus j sin pi by 2 means minus j.
minus j,
minus
এটা 0.
তাহলে minus j, I will write e to the power minus j pi by 2. Okay, into 2 times h1 sin omega, 2 times h2 sin 2 omega. Now if you look at this expression, see, this having phase minus pi by 2, this is a constant phase. Another important thing, if I write this equal to in for any general value of odd n can take any value. So for n general value, I will write n equal to 1 to n minus 1 by 2. Suppose n equal to 5, so it will become 5 minus 1 by 2. So 5 minus 1 by 2
4
means 2.
2
2. N equal to 1 to 2. So first value of n will be 1. So it becomes 2 h1 sin omega. And second value will be 2h2 sin 2 omega, 2h2 sin 2 omega. So this is in general for any value of n. This is also easy to remember. And this minus is absorbed to the power minus j pi by 2. This is also much simpler compared to symmetry about n minus 1. What is that? See, the symmetry about n minus 1, in that phase was a function of number of samples. But even if you are having the phase information in this kind of symmetry, but the phase is constant phase. Therefore, if phase is constant, so e to the power minus some j constant, that means is a linear phase, because e to the power j alpha is a linear phase. So that means this is not a problem, because some constant multiplication only. Therefore, what I am saying, that this kind of transfer function is simpler to deal with compared to symmetry about n minus 1 by 2. symmetry about n minus 1 by 2, this kind of transfer function is easier to handle using this kind of symmetry. Another important thing in this respect, that this kind of transfer function has one advantage. You have studied Hilbert transform in your analog design. Hilbert transform. Okay, in Hilbert transform you have seen one thing, that J signum omega into x of omega, right? So there when the phase factor J is essentially a 90-degree phase shifter. A 90-degree phase shifter. Hilbert transform is essentially a 90-degree phase shifter. 90-degree phase shifter operation. Cos will become sine, sine will become minus cos, like that. Therefore, this kind of application, this kind of transfer function is more important or more essential. However, in filter design aspect, also this is easier to handle compared to n-1 symmetry, because they are having either constant phase or no phase information. So phase, linear phase, which is an important criteria of a FIR filter design, that is not a big issue with respect to this kind of symmetry. Is it all right? Or if you have any doubt? If you have any doubt,
সিগনামের ওখানে যেটা বললেন আর এখানের সঙ্গে কি রিলেট করলেন
ওটা বলছি যে হিলবার্ট ট্রান্সফর্মের ট্রান্সফার ফাংশন হচ্ছে যে x of Hilbert transform of a signal, that is x of x cap of omega equal to minus j signum omega into x of omega. X of omega is the Fourier transform. Then Hilbert transform will be minus j signum omega into x of omega. So what I am saying, that when a transfer function is multiplied with some factor j, for such kind of thing, this kind of filter transform, you can use this transform as a Fourier. This is a Fourier transform. So this Fourier transform j terms is already included. So we can use that jx of omega in this transform with this kind of symmetry. If this kind of symmetry is there, then already you have calculated with jx of omega. This value is available with you. Okay, because this is j times some filter transform, not j times something. So if I say Hilbert transform x cap of omega minus j times signum omega x of omega, minus j x of omega is available with you. Once this is available, then we can substitute the value of signum omega to get the Hilbert transform. Now signum omega means omega greater than 0, it is 1, omega less than 0, it is become minus 1, right? If you remember these things, you have studied in SSBSC, single sideband subdesk area, and you have studied this thing in your signal system. Signal system you have studied for Hilbert transform. So signal system and those things are there in your 3rd semester and 5th semester course, like in, okay, fine. Now, is it all right? Whatever we have discussed about the transfer function and all this thing?
Yes, sir.
Okay. Now, you may ask one question, that is, why this is only for odd, why even is not there? Do you have this question? Do you have this question? तुम लोग तो पूछा नहीं? You have not asked?
কি স্যার?
Previously, when I was discussing the symmetry or antisymmetry about the point n-1 by 2, that is symmetry about n-1 by 2 or antisymmetry about n-2, previously what we are discussing, then we have discussed for odd and even. Is not it? Now, today I have discussed the symmetry or antisymmetry with respect to n equal to origin. Then I have discussed only odd. Then you should have asked why not even?
মানে স্যার ওই অরিজিনের সাপেক্ষে ইভেন্টে ডিস্ট্রিবিউট করা যাবে না বলে।
Very good. Yes, you are correct. You are correct. Amit is correct. With respect to origin, we cannot distribute this. For example, suppose n equal to 0 and capital N equal to 6, and I am assuming the symmetry condition with respect to origin, that is n equal to 0, h of minus n equal to h. Now with respect to origin, suppose n equal to 6, I can write minus 2 minus 1 0, I can write 1 2 3, okay, 1 2 3, or because 6 points only I have to take, so 1 2 3 4 5 6, or I can take h of minus 3, h of minus 2, h of minus 1, h0, h1, h2. Now, with respect to origin, if you look at here, here it is 2, here it is 3. So you cannot take a symmetry. Now, with respect to this, h equal to 0, here it is 3, here it is 2. Again, this symmetry cannot be maintained. Therefore, this such discussion that symmetry about origin, then you cannot distribute with respect to origin for even values of n. So, in other words, we cannot distribute the filter coefficient with respect to origin symmetrically about the origin. That's why this kind of symmetry does not exist for even value of the number of samples. Agreed?
Yes.
Similarly, suppose n equal to 6, n equal to 0 and h of minus 1 equal to minus n equal to minus of hn. In this case also, if I try to distribute with respect to origin, same problem will be happening, because with respect to n equal to 0, we cannot arrange symmetrically or equal number of points. Therefore, for even value of n, antisymmetric distribution also does not exist. Okay? If you have any doubt, then you can ask. Otherwise, I will tell you what are the different steps for designing filter. Do you have any doubt?
No.
No doubts. Now, I will be telling you what are the different steps of designing filter. I have not written here, but I am telling you the steps. If you have pen, you are having pen and paper with you?
হ্যাঁ
আছে
Yes, sir.
বাকিদের
হ্যাঁ
বাকিদের আছে কেয়া পেন আছে
Yes, sir.
okay, okay. So write down the design steps for designing a FIR filter. Steps for designing a FIR filter. Step 1. Step 1. From the given step 1, from the given problem, first identify the number of samples. From the given problem, first identify the number of samples for number of samples. Okay, that is n, capital N.
Yes.
Capital N. Next, second thing you write down, obtain desired
Step 2.
Step 2, obtain desired filter response. अच्छा ওখানে স্টেপ 2 দেখলে obtain লিখলেন না, তো obtain না লিখে ওখানে লেখো assume obtain এর জায়গায় লেখো assume the desired filter response on the basis of the given problem. On the basis of the given problem. Or step 2 to let me explain. On the basis of the given problem, what does it mean? Let me explain. On the basis of the given problem means, suppose we have to identify here what kind of filter you have to design. Whether it is a low pass filter, whether it is a high pass filter, whether it is a band pass filter or it is a band stop filter. On the basis of that, you have to assume the desired frequency response characteristics of the filter. Now, what are the desired response? কোনগুলো বলো তো? What are the desired response?
কি বলেন?
What are the desired response? Desired response টা কোথায় পড়িয়েছিলাম? Desired response মনে আছে? Desired response টা কোথায় বলেছিলাম? কোন লেকচারে? Which lesson I have discussed the desired?
It is the first lecture.
Huh? Desired.
কিছু কত নম্বর
I-
ফার্স্ট যেটা পাঠিয়েছে
This is probably the desired. Yes, these are the desired. Suppose if you have to design low pass filter, then you have to assume this is the desired response. This is the desired response. You have to design high pass filter, then this will be the desired response. And this is the band pass filter, so this is the desired response. And this is also thing, so this is also your desired response. Now, so once you know the desired response, then what is known to you? Hd of omega is known to you. Hd of omega is known to you, magnitude. This magnitude is known to you. Now, we will assume some linear phase e to the power j alpha omega, alpha equal to n minus 1 by 2. So in general, it will be magnitude c times e power minus j alpha omega, hd of omega. Agreed? So magnitude of this will be c over minus omega c to plus omega c. But phase is equal to e power j alpha omega, alpha equal to n minus 1 by 2. Now my question is that step 3, what we require? We have to find the hd of n, which is the inverse of hd of e power j omega. Now step 3 you write down, integrate or now find the inverse of hd of omega or hd of e power j omega to obtain hd of n.
Yes, sir.
Agreed? So hd of e power j omega is known. Now finding the inverse, I have got hd of n. Agreed?
Yes, sir.
Now, what is given? Number of samples n is given. Okay. Now step 4. Step 4, identify the window function given in the problem. Identify the window function given in the problem. If nothing is specified, then assume rectangular window.
If nothing is
Specified, then assume rectangular window. Step 5. Since hd of n is infinite in nature, because hd of n having non-zero values for infinite number of values of n, then hd of n has to be multiplied with window function with specified number of samples to make hd of n finite.
to make
hd n finite, that
স্টেপ
is
5 টা একবার প্রথম থেকে বলুন।
finite
hd of n finite, that is hn equal to hd of n into wn. ওকে, এই স্টেপ 5 টা কেউ একজন বলো, কে ও জিজ্ঞেস করছে, আরে বলো তো স্টেপ 5 টা বলো তো কেউ একজন যে লিখতে পেরেছো।
Since HD of n is infinite in nature, because HD of n has non-zero values for infinite values of n, then
Yes.
HD has to be
Yes.
multiplied with the window function with specified number of sample to make HD of n finite. That is h of n equal to HD of n
SD open. Okay.
into W.
into window wn.
এই যে 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 বলছে শুনতে পেলে, যে জিজ্ঞেস করছিল আরেকবার বলতে, সে শুনতে পেয়েছো?
হ্যাঁ স্যার।
শুনেছো তো? ঠিক আছে। তাহলে নাও ইউ হ্যাভ গট h of n is a finite. h of n টা ফাইনাইট হয়ে গেল। ওকে, নাও
স্যার
হ্যাঁ বলো।
স্যার বলছিলাম লাস্টে দ্যাট ইজ এইচ অফ এন ইজ ইকুয়াল টু কি বললেন?
h of n equal to hd of n multiplied by w of n.
ঠিক আছে স্যার।
Okay, now
ইয়েস
now obtain discrete time Fourier transformation of step 6. Obtain discrete time Fourier transformation of h of n to obtain the frequency response of the filter over 0 to pi, over 0 to pi, because minus pi to pi my range of vision I have fixed. So I will draw only positive side, negative side I don't draw. Positive side means I have to find the filter response 0 to pi, and I should get, so step 6 you have written, what you written, step 6?
Now
Obtain
ETFT of HN to obtain the frequency response of the filter over 0 to pi.
that's what. Now let me explain. So step 6 what you have got, hd of e power j omega. So hd of j omega, it is a function of omega. Then if we put different values of omega equal to 0, omega equal to pi by 4, omega equal to pi by 3, omega equal to pi by 2, omega equal to pi for different values, pi by 8, pi by 16, like that. For every values 8 or 10 values we have to take, and we have to take the value of hd of omega, like what you have done in step 6. Okay, then step 7, plot the values using a graph paper. Step 7, plot the values using a graph paper. Step 7. Step 8, last step, realize the filter using known form such as direct from 1, direct from 2, etc. after obtaining hz. Okay, so with these 8 steps your filter design steps are completed. Okay, so if you have any doubt you can ask, otherwise from next class, I think in Friday I will start filter design. I will discuss at least 4 to 5 filter design problem, covering all options. Like you are having different kind of window functions, like Bartlett window, Hamming window, Hanning window. That window functions, these names are not nothing to worry about. There are some window functions that will be specified in the problem. So all possible window what is there in your syllabus, I will discuss at least 5 or 6 design problem, and on the basis of 5 or 6 design problem you will design 5 or 6 filters. And once we design all 12 filters, you should be in a position to design any FIR filter by the end of this class. Okay, so I will take another 4-5 class on filter design, FIR filter design. And
sir,
বলো, any doubt?
হ্যাঁ বলছি স্টেপ 3 টা মিস হয়ে গেছে মনে হয়, বলবেন একবার?
সেফটি কি ছিল বলো, আমার তো মনে নাই কি বলেছিল সেফটিটা, কি বলেছে, কি ছিল বলো।
Find the inverse of hd of omega or hd of e to the power j omega to obtain hd of n.
বাস তো বুঝা গেল।
হুম
বাস, তাহলে with this I am having less than 1 minute, so I want to close. Until then, thank you again.
থ্যাংক ইউ।
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Okay.